Hello and welcome to Controllerstech. Let's say I want to perform multiple tasks where I need to read a sensor, update the display, and receive some data from the UART as well. If we use the regular superloop to do this, there are three main problems that we can face. First, Hall delay does not pause just one thing. It freezes the entire CPU. So while you're waiting 500 milliseconds for the display update, your UART may lose data and your sensor may miss readings. Second, multiple timing requirements start to conflict with each other. A 200, 500, or 1000 milliseconds delay does not compose cleanly in one loop. Third, any task that needs to wait without blocking the loop must become a complex state machine. The code becomes unreadable very quickly. The while loop works for one or two timing requirements, but after that you need something better. This is where an RTOS comes in. An RTOS, or real-time operating system, is a lightweight operating system designed for embedded systems. Its main job is scheduling, deciding which piece of your code runs and when. Instead of one loop doing everything, you write independent tasks, each focused on a single job. A sensor task, a display task, and a UART task. Each one looks like its own small program with its own infinite loop. The RTOS runs them all, switching between them thousands of times per second, so fast that they appear to run simultaneously. Today we will start a new video series on FreeRTOS. This series will be focused on implementing CMSIS, RTOS version 2, rather than using the native FreeRTOS APIs directly. Throughout this series, we will cover tasks, semaphores, mutexes, queues, task notifications, software timers, and much more. We will understand not only how to configure them in STM32 CubeMX, but also how they work internally and how to use them properly in real embedded projects. Before writing the code, you need to understand what a task actually is, because it is not just a function. A task is an independent program. It has its own stack, its own saved CPU registers, and its own program counter. When the RTOS pauses a task mid-execution, every register, every local variable, and every byte of its state is saved. When it resumes, it continues exactly from that point, as if it was never paused. Internally, the RTOS tracks every task using a task control block, TCB. It is basically a small data structure that stores the task's stack pointer, priority, current state, and timing information. The scheduler reads this to manage everything. This is why every task has its own infinite loop. If a task returns, it will be deleted by the RTOS. That is why we never want a task to return, so we create an infinite loop for it intentionally. There are mainly four states you will see for a task. The first one is running, which means the task currently owns the CPU. The ready state means the task wants to run and is waiting for the scheduler. Blocked means the task is waiting for a delay or a resource. It does not use any CPU at that point. Terminated means the task has been deleted. Basically, it is gone forever. The scheduler always picks the highest priority ready task. Blocked tasks are completely skipped. No CPU time is wasted on waiting. Now we understand what an RTOS is and what a task is. But the main question is, where does CMSIS RTOS come into the picture? There are many RTOS in the embedded world: FreeRTOS, RTX5, ThreadX, Zephyr, and others. Each has its own API. Code written for FreeRTOS doesn't compile against RTX5 without rewriting everything. CMSIS RTOS is an abstraction layer, a standardized API defined by ARM that sits on top of any compatible RTOS kernel. It does not schedule anything. It simply provides a consistent set of function names. For example, OS thread new calls X task create in the case of FreeRTOS. OS delay calls V task delay, and so on. This is how CM/sys/RTOS is arranged. On top, you have your application code, which calls the CM/sys/RTOS APIs. These then call the FreeRTOS or any other kernel APIs, which actually control the STM32 hardware. The benefit of using CM/sys/RTOS is that your application code becomes portable. If ST ships your project with FreeRTOS today and you switch to another kernel like ThreadX or RTX5 tomorrow, your code will still call OS thread new. It will not change. Only the underlying kernel wrapper changes, while your application code remains exactly the same. Now that we have a basic idea of what an RTOS is, why it is used, and how CM/sys/RTOS acts as an abstraction layer on top of the native RTOS APIs, let's create a quick project in STM32 CubeMX to implement it. I am going to use the Nucleo L496 for this project. So let's start CubeMX and access the board selector. I am using the Nucleo L496 variant P, which is the 144-pin Nucleo board. Let's start the project. Do not start the peripherals in the default mode. Some of the pins are configured by default. Let me first clear all the pins so that we can build everything from scratch. We will start with the clock configuration. This Nucleo board does not have an external crystal for the system clock, so I am going to use the internal oscillator. Therefore, we will not enable the HSE or LSE clocks. Go to the Clock Configuration tab and set the source as the high-speed internal oscillator. We will use the PLL to run the system at the maximum possible 80 MHz. That is all we need here. Now go back to pin configuration. Go to sysdebug and enable serial wire debugging. This will help us debug the project when needed. Next, we will enable FreeRTOS. It is located inside the middleware section. Expand it, click on FreeRTOS, and enable CM/sys version 2. This is the newer version, so we will use it in this video series. There are many parameters available for configuration, but today we will keep things simple. I will explain only the few that are required for now, and as we proceed through the series, we will cover the others. The first one is the tick rate, which is set to 1000 Hz. A tick rate of 1000 Hz means the sys tick fires 1000 times per second, that is once every 1 millisecond. This gives us a 1 millisecond resolution. In FreeRTOS, this effectively allows us to create delays with a minimum resolution of 1 millisecond. Next is the minimal stack size, which is set to 128 words. This value is in words, not bytes. Since one word on a 32-bit Cortex-M is 4 bytes, 128 words equals 512 bytes. Each task in an RTOS has its own stack. The stack stores local variables, function calls, return addresses, and the CPU registers during context switching. When the scheduler switches tasks, it saves and restores data using this stack. If the stack size is too small, a stack overflow can occur, leading to unstable or unpredictable behavior. That is why a minimum stack size is defined, to ensure every task has enough memory to run safely. Next, look at the total heap size, which is currently set to around 3 kilobytes. All RTOS objects such as tasks, timers, semaphores, queues, and other kernel resources allocate memory from this heap. Whenever we create a new RTOS component, memory is taken from this shared heap space. As the project grows and more RTOS features are added, the heap requirement will increase, so we may need to adjust this value later. For now, since this is a simple project, we will keep it at 3000 bytes. Now go to Tasks and Queues, and you will see one default task already created. Double-click it to see its properties. The task name is default task. We do not use the task name in our code, it is only for identification. The priority is set to normal. If you expand the list, you will see many priority levels available. For now, we will keep it at normal. We will explore priorities more when we create multiple tasks. The stack size for this task is set to 128 words, which is the minimum allowed value. Even though the task is empty, this is the minimum stack size required. The entry function is start default task. This is the main task function where we will write our application code. It is automatically generated by CubeMX, and we will modify it later in Cube IDE. We are not passing any parameters to this task, so the argument is set to null. If needed, we could pass a pointer to data or configuration parameters here. The memory allocation is set to dynamic, which means the RTOS will automatically allocate the required memory, such as the task stack and control block, from the heap at runtime. If you check the FreeRTOS heap usage, you can see that 632 bytes are already used by the default task. Out of these, 512 bytes are allocated for the task stack. The remaining bytes are used by the task control block, and other internal RTOS structures required to manage the task. The rest of the heap memory is still available and can be used when we create additional tasks, queues, semaphores, or other RTOS objects. For this demonstration, I am going to blink one LED. The Nucleo L496 already has one onboard LED. From the schematic, we can see there is a blue LED connected to pin PB7. So we will configure PB7 as an output to control this LED. Go back to CubeMX and set PB7 as a GPIO output pin. That is all the configuration we need. Now go to Project Manager, give the project a name, I am calling it RTOS Part 1, and make sure the IDE is set to Cube IDE. Then click Generate Code. You may see two warnings. The first suggests not using sysTick as the default time base. The second suggests enabling the new LibReentrant option. Click No for now, and let's configure them properly. First, enable new LibReentrant in the FreeRTOS advanced settings. This ensures that standard C library functions like printf work safely in a multitasking environment. Next, go to sys and change the timebase source from sysTick to a timer. We can use any of the available timers for the timebase, but it is better to use timer 6 or timer 7. These are basic timers and do not have advanced features like input capture, output compare, or PWM. Since they are simple and usually unused in most projects, they are ideal for providing the HAL time base when working with FreeRTOS. That is all we need to change. Now click Generate Code, and you will see that the project is generated without any issues. Finally, import the project into Cube IDE. Locate the project folder generated by the CubeMX, and click Finish. Alright, the project has been imported to Cube IDE, and here you can see the main file of the project. The FreeRTOS files are located under middleware third-party FreeRTOS. Inside the main.c file, you will see the default task handle, and its attributes defined, exactly as we configured them in CubeMX. Such as the task name, stack size, and its priority. Here we have the entry function. As I mentioned earlier, this is the main task function where we will write our application code. This function will be defined later in the file, and we will add our task implementation inside it. Inside main function, after initializing the peripherals and clocks, the code calls OS kernel initialize. This function prepares the RTOS kernel before any tasks are created or started. It initializes the scheduler, internal data structures, and memory management so that tasks and other RTOS objects can be created safely. Then there is space for initializing mutexes, semaphores, timers, or queues, which we are not using right now. After that, the task is created using OS thread new. The parameters of this function are entry function of the task, the data to be passed to the task, and the thread attributes, which are already defined above. Finally, OS kernel start is called. This function starts the RTOS scheduler and begins multitasking. From this point onward, the scheduler takes control of the CPU and starts executing the created tasks based on their priority. After OS kernel start is executed, control does not return to main function. Any code written after this function call will not run, because the RTOS is now managing the system. Internally, OS kernel start calls vtask start scheduler, which is the native FreeRTOS API. Now scroll down and find the start default task function. Inside it, you will see a user code section and an infinite loop. The infinite loop ensures that the task never returns. If a task function exits, FreeRTOS will automatically delete that task. That is why every task must run inside an infinite loop. Inside this loop, we will blink the LED by calling hold GPIO write pin to set and reset pin PB7. For the delay, we will use OS delay to create a 1-second delay between setting and resetting the pin. This means the LED will turn on for 1 second and then off for 1 second. Now you may ask, how is this different from using HAL delay? HAL delay blocks the entire CPU until the delay is complete. Internally, it waits in a loop until the required time has passed. During this time, the CPU keeps checking and effectively wastes cycles doing nothing else. On the other hand, OS delay does not waste CPU cycles. It puts only the current task into the blocked state for the specified time. While this task is waiting, the scheduler is free to run other tasks. That is the key difference. HAL delay blocks the entire CPU, whereas OS delay blocks only the current task. Now build the project. There are no errors here, so let's flash the project to the board. You can see the blue LED blinking every 1 second. This confirms that a basic RTOS project is now set up and running successfully. We have configured FreeRTOS in CubeMX, generated the project, initialized the kernel, created a task using OS thread new, and started the scheduler using OS kernel start. The task is executing independently, and the LED is blinking using OS delay, which proves that the scheduler is managing the CPU correctly. At this point, you have understood the complete flow of a minimal RTOS-based project, from configuration to execution. You also saw the fundamental difference between a traditional superloop approach and an RTOS-based design. In a superloop, everything runs sequentially and blocking delays freeze the entire system. In contrast, an RTOS allows multiple tasks to coexist, and when one task is waiting, others can continue executing. This is the core advantage of using FreeRTOS in embedded systems. We covered the RTOS configuration and ran a single LED blinking inside one task. But real embedded systems need more than that. They require several independent jobs running simultaneously, each with its own priority, its own timing, and its own dedicated role in the system. In this video, we are going to create multiple tasks, assign priorities to each of them, and control the task lifecycle using the CMSys RTOS API. We will also see how a high priority task can preempt a lower priority one, and why the reverse is simply not possible. Before we dive into the code, let me give you a clear picture of what we will be doing in this video. I am going to create 4 different tasks, each with a different priority level. Task 1 will blink one LED, and will have the lowest priority of the four. Task 2 will blink a second LED, and will have a priority higher than Task 1. Task 3 will blink a third LED, and its priority will be higher than both Task 1 and Task 2. Task 4 will control the life cycle of one of the remaining tasks, and it will hold the highest priority of them all. First, we will observe what happens when Task 1 is performing a long operation. We will check whether the higher priority tasks are able to preempt it and continue blinking their LEDs at the predefined rate. After that, we will intentionally delay the processing of Task 3 and observe whether Task 1 and Task 2 can preempt it and blink their LEDs at the desired rate. For this tutorial, I am going to continue building on the project we created in the previous video. Here you can see the RTOS Part 1 project already loaded in STM32 Cube IDE. The first thing we will do is rename the project to Part 2. Make sure the Update References checkbox is checked, so the project name gets updated in all the required places as well. The renaming is done. Now let us delete the previously generated configuration, and I will also rename the IOC file accordingly. With that, everything is properly set up for Part 2. Before we begin configuring the project in Cube IDE, let us take a quick look at the schematic of the STM32 Nucleo L496 development board. As mentioned in the previous tutorial, the blue LED is connected to pin PB7, and we will continue using this LED today. In addition to the blue LED, the board also features a red LED, which is connected to pin PB14. We need 3 LEDs for this project. The third one is a green LED, which is connected to pin PC7. So now we have all 3 LEDs ready, one for each of the 3 tasks. Let us open STM32 Cube MX and load our Part 2 project. As mentioned earlier, this is essentially the Part 1 project with only the name changed to Part 2. Pin PB7 is already configured as an output. Let us rename it to Blue LED so that it is easier to identify while writing the code. Next, let us set pin PB14 as an output as well, and rename it to Red LED. Similarly, pin PC7 will be set as an output and renamed to Green LED. With that, all 3 LED output pins are now configured. Let us navigate to Middleware, then FreeRTOS, and open the Tasks tab. In the previous project, we only had one task, which was the default task. I am going to rename it to Task 1 and set its priority to low. Now, although I could use below normal, since below normal is technically lower than normal priority, I am using low here just to keep the naming consistent and easy to follow. The stack size will remain at 128 words, and the entry function will be renamed to Start Task 1. Now we will create the remaining tasks in the same way. Click the Add button to create a new task. I will name this as Task 2 and set its priority to below normal. This priority is still higher than Task 1, which is set to low. Next, we will add another task, name it Task 3, and set its priority to normal. All tasks are kept at a stack size of 128 words, since we do not need to perform heavy operations inside them, we are simply blinking LEDs. Finally, Task 4 will be created with a priority of above normal, and its stack size will also remain at 128 words. So now we have 4 tasks in total. To summarize the priority order, Task 1 has the lowest priority set to low, followed by Task 2 at below normal, Task 3 at normal, and Task 4 at above normal, making it the highest priority task of them all. If you check the FreeRTOS heap usage section, you will see that all 4 tasks occupy the same amount of memory, and we still have 472 bytes remaining. This is more than sufficient, so no changes are needed here. Let us now click Generate Code to generate the project files. Alright, with that done, let us head back to STM32 Cube IDE. As you can see, all 4 task functions have been created inside the main function. Now it is time to write the actual code inside each of these tasks. Instead of manually setting and resetting the pin state, I am going to use the toggle pin function, which automatically switches the pin between high and low with each call. Inside task 1, we will toggle the red LED, with a delay of 1 second. Keep in mind that task 1 has the lowest priority of all 4 tasks. Inside task 2, we will blink the blue LED with a delay of 500 milliseconds. Similarly, inside task 3, we will blink the green LED with a delay of 200 milliseconds. We will leave task 4 unchanged for now, as we know we will be modifying it in a later step. Let us first test what we have so far. We will build the project, there are no errors, so let us go ahead and flash it to the board. As you can see, all 3 LEDs are now blinking on the Nucleo board. You can focus on one LED at a time to observe each one individually. You will notice that the red LED blinks every 1 second, the blue LED blinks every 500 milliseconds, and the green LED blinks every 200 milliseconds. All 3 tasks are working correctly, each blinking its respective LED at the predefined rate. Now we will take this a step further. We are going to block the processing of task 1 and observe whether task 2 and task 3 wait for it to finish, or whether they preempt it and continue blinking their LEDs at the defined rate. Inside task 1, I am declaring a variable called wait and initializing it to 50 million. After the delay, the code enters an empty while loop that keeps decrementing this variable on every iteration until it reaches 0. During this entire time, the CPU is stuck inside this loop, doing no useful work. It is simply burning through clock cycles waiting for the counter to hit 0. This simulates a situation where a low priority task is hogging the CPU with a long blocking operation. Now let us see whether this empty while loop inside task 1 has any impact on task 2 and task 3, or whether they continue to perform their operations as expected. Let us flash this updated project to the board. As you can see, the red LED is now blinking at a slower rate than 1 second. This confirms that the empty while loop inside task 1 is directly affecting its own blinking speed. However, the blue and green LEDs are still blinking at their predefined rates, the blue LED every 500 milliseconds, and the green LED every 200 milliseconds. They are completely unaffected by the empty while loop we added inside task 1. So why does this happen? When task 1 gets stuck inside that empty while loop and task 2's delay expires, task 2 simply preempts task 1, performs its job, and goes back to the blocking state. The same applies to task 3, it does not need to wait for task 1 to finish. It preempts task 1, blinks its LED, and returns to blocking. This is because task 2 and task 3 both have higher priorities than task 1. They do not need to wait for task 1 to enter the blocking state on its own, they can interrupt it at any point, complete their operation, and step aside. Task 1, on the other hand, can only run when both task 2 and task 3 are in the blocking state. That is why task 1 is still running, but at a much slower rate than before. Now let us move that empty while loop into task 3 and see what changes. Since task 3 has the highest priority among the 3 LED tasks, task 1 and task 2 cannot preempt it. So if task 3 gets stuck running that empty while loop, task 1 and task 2 have no choice but to wait until task 3 is completely done. Let us flash this updated code to the board. As you can see, all 3 LEDs appear to be blinking together. Let me explain exactly what is happening here. Task 3 toggles its LED and immediately calls OS delay, which puts it into the blocking state for 200 milliseconds. During that window, task 1 and task 2 get their turn to run, and they both toggle their LEDs on. However, since task 3 only has a 200 millisecond delay, it wakes up first and preempts both task 1 and task 2. At this point, the LEDs of task 1 and task 2 are still on, and both of those tasks are now sitting in the background, waiting for their turn. Task 3 is now running the empty while loop. Task 1 and task 2 are ready to run and want to toggle their LEDs off, but they cannot. Task 3 is still executing and holds a higher priority. They are forced to wait. Once task 3 finally finishes the loop, it toggles its own LED off and calls OS delay again. During that 200 millisecond blocking period, task 1 and task 2 finally get control and toggle their LEDs off as well. Then task 3 wakes up once more, preempts them both, and the entire cycle repeats from the beginning. Because task 3 holds the highest priority, task 1 and task 2 are forced to synchronize with it. They can only run during the periods when task 3 is in the blocking state. And that is the key takeaway from this demonstration. A higher priority task can preempt a lower priority one at any point in time, but a lower priority task can never do the same in return. Now we will leave task 3 as it is and use task 4 to demonstrate how to control the life cycle of a task. Inside task 4, I am calling OS thread suspend to suspend task 3, then waiting for 5 seconds, and then calling OS thread resume to bring it back. Since task 4 has the highest priority of all, it can preempt task 3 even while task 3 is stuck running its empty while loop. This means as soon as task 4 gets its turn to run, it will suspend task 3 immediately. When a task is suspended, it is completely removed from the scheduler and will not receive any CPU time at all. However, its stack and internal state are safely preserved inside the FreeRTOS kernel, meaning the task still exists in memory. It has not been deleted. It has simply been taken off the scheduling timeline until something explicitly resumes it. Let us flash this to the board and observe how it behaves on the Nucleo board. As you can see, the green LED stays on for quite a long time. Here is what is happening. When the green LED turns on, task 3 enters its empty while loop, and while it is still running that loop, task 4 preempts it and suspends task 3 for 5 seconds. Task 3 is now paused with the green LED left in the on state, and it will remain exactly like that until it is resumed. While task 3 is suspended, task 1 and task 2 are free to run without any interference. You can now see the red and blue LEDs blinking at their normal rates again. Once task 3 is resumed, it will toggle the green LED off and start running the empty while loop once more. Task 4 will then preempt it again and suspend it for another 5 seconds, during which task 1 and task 2 can continue running freely. So using suspension and resuming, we have full control over when a task runs and when it is completely taken out of the picture. When task 3 is suspended, it is no longer part of the scheduling timeline, which allows task 1 and task 2 to run as if task 3 does not exist at all. Now, alongside suspension, there is another important function called OS thread terminate. Unlike suspension, this function completely and permanently removes the task from the system. Once a task is terminated, it cannot be resumed. You would have to create it all over again from scratch. Because of this, task termination is rarely used in practice, and suspension is generally the preferred approach when you need to temporarily stop a task. One case where termination does make sense is when a task is only meant to perform a one-time initialization at startup, and then remove itself from the system once that job is complete. In addition to what we use today, CMSIS, RTOS version 2 provides several other functions that give you a more detailed view of what is happening inside FreeRTOS at runtime. Here is a quick overview of some of the commonly used thread functions available. OS thread getID returns the ID of the currently running thread. OS thread getState allows you to query the current state of any thread at any point, whether it is running, ready, or blocked. We already used OS thread suspend and OS thread resume in this video. Suspend removes a thread from the scheduling timeline until something explicitly brings it back, and resume does exactly that. It places the thread back into the scheduler so it can run again. OS thread terminate permanently deletes a thread and frees the memory it was using. As discussed earlier, once a thread is terminated, it is gone for good, and cannot be brought back without recreating it. Finally, OS thread get priority reads the current priority of a thread, and OS thread set priority allows you to change that priority at runtime. This can be particularly useful in situations where the importance of a task needs to shift dynamically based on the current conditions of the system. Now that we have multiple tasks running in the system, the next step is to allow these tasks to communicate with each other. For example, we might want to send some data from one task to another. A common mistake when implementing this is using a global variable to share data between tasks. For example, say I have a structure that will be updated by two different tasks, and it will be consumed by a third task. Now let's say task 1 updates the data in the structure, and we expect the consumer task to read this data. At the same time, task 2 can also update the data in the same structure, and the consumer task will read that data as well. The problem here is that a race condition can occur. In this situation, the data can get corrupted. The consumer task may end up reading the data written by task 2, even though it was actually expecting the data from task 1. To solve this issue, we should use a more reliable method of communication between tasks. FreeRTOS provides queues specifically for this purpose. Think of a queue as a small buffer that can store multiple messages sent by different tasks. In this example, we will configure the queue to hold 10 elements. So you can imagine it as 10 slots, where each slot can store one message. Now suppose task 1 generates some data and sends it to the queue. The data will be placed in the first empty slot of the queue. Next, if task 2 generates data and sends it to the queue, it will be placed in the next slot. Both tasks can continue sending data, and the queue will keep filling up one element at a time, until all 10 slots are filled. If the queue becomes full, then any new message sent by task 1 or task 2 will have to wait until some space becomes available in the queue. Now on the other side, we will have a receiving task. Its job is to read the messages from the queue. Whenever the receiving task reads one message, that message is removed from the queue, which means one slot becomes free again. Another important thing about queues is that they follow the FIFO rule, which stands for first in, first out. This means the first message that enters the queue will also be the first one to leave it. So if task 1 sends a message first and task 2 sends another message after that, the receiving task will first read the message from task 1, and then the message from task 2. Now let's say we have a queue. Task 1 writes the data into the structure and then pushes that structure into the queue. The consumer task will read the structure from the queue. If task 2 wakes up and writes new data into the structure, it will also push its structure into the queue. This data will simply be added to the queue as another element. So the consumer task will first read the structure sent by task 1, and then it will read the structure sent by task 2, in the same order they were placed in the queue. In this video, we will see how to create a queue, how to send data to the queue, and how to receive data from it. We will also look at what happens when the queue becomes full, and how to handle different situations when the queue is full or empty. Let's start with the project we created in part 2. Here you can see that the project has already been loaded into the IDE, and it is the same project we used in the previous video. The first thing we will do is rename it to part 3. While renaming, make sure to check update references, so that all the relevant names are updated automatically in the project. Alright, the renaming is done. Now we will delete the debug configuration and also rename the IOC file so that it matches the project name. Before we proceed further, let me quickly give a brief overview of the example we are going to implement in this video. We will create two different tasks, and both of them will write data into a common structure. After updating the data, each task will push that structure into a queue. There will also be a receiving task, which will read the data from the queue and print it through UART. For printing, we will use the printf function. This will make debugging easier, and it will also be useful for debugging in the upcoming videos. Now let's take a quick look at the schematic of the L496 board. Since this is a Nucleo board, we can use the virtual COM port to route the UART data through the ST-Link USB connection. Here you can see that ST-Link RX is connected to low-power UART1 TX, and ST-Link TX is connected to UART1 RX. These correspond to pins PG7 and PG8, so we will keep this in mind while configuring the UART in CubeMX. I am also going to use a button to update the data in the structure. The button will be connected between pin PA3 and ground. The pin will be pulled high by default, and when the button is pressed, it will be pulled low to ground, indicating that the button has been pressed. Now let's open CubeMX to configure the project. Load part 3 into CubeMX. First, disable all the LED pins that we configured in the previous project, since we will not be using them anymore. Next, configure pin PA3 as GPIO input, since this is where the button will be connected. Now go to the GPIO configuration, and set the pin to pull-up mode. This ensures that the pin remains high by default, and when the button is pressed, it will be pulled low to ground. Now go to connectivity and enable low-power UART1 in asynchronous mode. We will use this UART to route the printf output to the computer. By default, the pins PC0 and PC1 are assigned for this UART. However, as we saw in the schematic, we need to configure PG7 and PG8 instead. So set PG7 as UART1 TX and PG8 as UART1 RX. I am going to keep the baud rate at 115200. The word length will be 8 bits, with no parity and one stop bit, which is the standard UART configuration. Now go to Middleware FreeRTOS and open Tasks and Queues. There are 4 tasks from the previous project, but we don't need 4 anymore. We will work with 3 tasks, so delete the 4th task. Let's modify task 1 first. Task 1 will send data to the queue, so I will keep its priority normal. The stack size will be 128 words, since there is not much happening inside this task. It will simply load data into a structure and send that structure to the queue. Similarly, task 2 will also have the same normal priority, and the same stack size. It will also push data into the queue. Now task 3 will be the receiving task, which will read data from the queue and print it via UART. Since this task receives the data and performs the printing operation, I want its priority to be higher than normal. We do not want task 1 and task 2 to preempt this task while it is performing the printing, otherwise the output on UART could get corrupted. Normally we would protect shared resources like UART using Semaphores or Mutexes, but since we have not covered them yet, I will simply set this task's priority to high. This ensures that task 1 and task 2 will not preempt the receiving task while it is printing. Since we are using printf, we also need a larger stack size. Set it to at least 512 words, which is about 2 kilobytes. The printf function requires more stack space, so you should adjust it accordingly. You may try lower values, but make sure to test it properly. After doing this, you will notice an error in the heap usage, showing that the available heap has been fully utilized. So go back to parameter configuration and increase the heap size. I will set it to around 5 kilobytes, and now the error disappears. We now have enough heap available. Inside the same tab, we also have the option to add a queue, so let's add one. I will name it message queue. The queue size defines how many elements the queue can store. We do not need a very large size, but since two different tasks will be sending data to the queue, let's keep it at 10. This means both tasks can send up to 10 elements in total, after which the queue will become full. Once the receiving task reads data from the queue, space will become available again. The item size represents the size of the data being stored in the queue. You can use data types like integers, characters, 32-bit integers, or any other type depending on what kind of data you want to send. In this example, I will use a structure that contains two elements: an 8-bit unsigned integer, and a 32-bit unsigned integer. Since we cannot define a structure type directly in CubeMX for the queue item, we will manually modify it later in the code. The allocation will be dynamic, so the memory will automatically be taken from the heap. If you check the heap usage, you can see that the message queue is consuming 132 bytes. Out of these 132 bytes, about 40 bytes are used by the queue items, and the rest is used for the internal queue management. Since we still have sufficient heap available, this configuration is good to go. That is all we need to configure here. Now click Generate Code to generate the project. Now let's go back to the IDE. Inside the main function, you can see that a message queue has been created along with 3 different tasks. Also note that the data size of each queue element is currently set to 32-bit integer, just like we configured in CubeMX. As I mentioned earlier, I am going to create a structure that will contain 2 data types: an event ID of 8-bit unsigned integer type, and a timestamp of 32-bit unsigned integer type. Task 1 and Task 2 will write their data into this structure. Now, since we want to transmit this structure to the queue, we cannot keep the queue element type as a 32-bit unsigned integer. This is the difference between a simple queue and a structure queue. If you only want to send a single 32-bit value, you can keep the queue type as 32-bit unsigned integer. But since we want to send a structure, we need to change the queue element type to our message structure. The queue will still contain 10 elements, but now each element will be one structure. So in total, the queue can store 10 structures at a time. As I mentioned earlier, we will use printf to print the data to the serial console. For this, we need a custom function that routes the printf output through UART. Inside this function, we will call HAL UART transmit to send the data through UART, one character at a time. So whenever printf prints something, it will internally call this function, and that function will transmit the data through UART. Now let's write the task functions. First, we define a local message structure that will store the data which needs to be sent to the queue. Inside the infinite loop, we check if the button is pressed. Since the pin is pulled high by default and goes low when the button is pressed, we will check if pin PA3 is low. If the button is pressed, we store the data inside the message structure. The event ID is set to 1, indicating that this event is generated by task 1. The timestamp is obtained using the function HALGetTick. After storing the data inside the structure, we call OSMessageQueuePut. This function is used to put a message into the queue. The parameters are queue handle, to which we want to send the message. Message pointer is the address of the structure we just created. And message priority defines how urgent the message is. In CMSysOS queues, messages can be assigned different priorities. Messages with higher priority are placed ahead of lower priority messages in the queue. So if multiple messages are waiting in the queue, the ones with higher priority will be read first. In our example, we will simply keep the priority 0, since this is not a priority-based message. The last parameter is the timeout. This defines how long the function should wait if the queue is full. For example, If the timeout is set to 1 second and the queue is already full, the function will wait for up to 1 second for some space to become available in the queue. If the queue does not become empty within this time, the function will exit and return a failure code. If we set the timeout to OS wait forever, the function will wait indefinitely until space becomes available in the queue. This can be useful in situations where the message must be sent, no matter how long it takes. On the other hand, if the timeout is set to 0, the function will not wait at all. It will check the queue. If there is space, the message will be added, otherwise, the function will return immediately with a failure code. After sending the data to the queue, we add a small delay. This helps with button debouncing, and also ensures that the task does not run continuously without yielding the CPU. Task 2 will have a similar logic. It will also push data into the queue. Here, we will first define a local message structure. However, instead of checking the button, this task will simply load data into the queue every 1 second. I am using a different event ID to indicate that the data is coming from task 2. I am also converting the timestamp to seconds, just to clearly differentiate it from the data generated by task 1. After storing the data inside the structure, we again call OS message queuePut, to place this structure into the queue. This loop will run every 1 second. So basically, if the button is not pressed, task 2 will still send data to the queue every second. If the button is pressed, then task 1 will also start sending data to the queue. Now let's look at the receive task. The job of the receive task is to read data from the queue and print it on the serial console. So here as well, we first define a local message structure. Next, we call the function OSMessageQueueGet. This function reads data from the queue and stores it in the message structure that we just defined. The parameters are similar to the previous function, but their behavior is slightly different. The timeout parameter works as follows. If we set the timeout to 0, the function will immediately check the queue. If data is available, it will read the data, otherwise, it will return an error code. If we use OS wait forever, the function will wait indefinitely for data to arrive in the queue. If the queue is empty, the task will be blocked until some data is written to the queue. As soon as data arrives, the function will read the data, store it in the message structure, and return the success code, which is OS OK. So if the data read is successful, we will print the data to the serial console. Here, I am printing both the event ID and the timestamp. That is all we need to do. Now let's build the project. We have an error related to the definition of printf. To fix this, we need to include the standard IO header file in the main file. After including it, all the errors are gone, and the project builds successfully. Now we are ready to test the project. Let's flash the code to the board. Now open the serial console to view the output. Make sure that the console configuration matches the UART settings we configured earlier in CubeMX. Here you can see event ID 2 being printed continuously every second on the console. This data is coming from task 2, which is periodically sending messages to the queue. You can also notice that the timestamp is in seconds, which is how we configured it in task 2. Now when I press the button, the data from task 1 is also printed immediately. You can identify it by event ID 1, and the timestamp is in milliseconds. So at this point, both tasks are sending data, and the receive task is reading that data from the queue and printing it on the console. This shows that the queue is working correctly and the communication between tasks is happening properly. Let's also take a quick look at some other queue-related functions available in CMSys OS version 2. We have already seen two important functions. OS message queuePut is used to put data into the queue. OS message queueGet is used to retrieve data from the queue. Now let's look at a few additional functions. OS message queue get capacity. This function returns the total number of elements that the queue can hold. For example, in our case we configured the queue to store 10 elements, so this function will return 10. OS message queue get message size returns the size of each message stored in the queue. OS message queue get count returns the number of messages currently waiting inside the queue. For example, if task 1 and task 2 both push one message each, and the receive task has not read them yet, then the queue will contain 2 messages, and this function will return 2. So it simply tells us how many messages are currently waiting in the queue. OS message queue get space returns the number of free spaces available in the queue. Continuing the previous example, if 2 messages are waiting in the queue, there are 8 empty spaces available, and this function will hence return 8. Now let's see how these functions can be used in practice. Before reading a message from the queue, we can call OS message queue get count. This function tells us how many messages are currently waiting in the queue. If the value is greater than 0, then we proceed with OS message queue get to read the data. Otherwise, we simply skip the read operation. This approach allows us to avoid using a blocking call while reading data from the queue. Similarly, before pushing data into the queue, we can check if the queue has free space available by calling OS message queue get space. This function returns the number of available spaces in the queue. If the value is greater than 0, we can safely push the message into the queue. Otherwise, we can handle the situation differently, depending on the application. There is one final function, OS message queue reset. This function resets the entire queue. It removes all the messages currently stored in the queue, effectively emptying it completely. So this is how inter-task communication works using queues. Queues provide a much safer and more structured way of transmitting data between tasks compared to global variables. As mentioned earlier, using global variables can easily lead to race conditions, especially as the project becomes more complex. Using queues helps avoid these problems and provides a more reliable communication mechanism between tasks. Queues are well suited for transferring data, but sometimes tasks simply need to coordinate with one another. For example, if one task is using a peripheral, the other task must wait, otherwise, the data being transferred to that peripheral will get corrupted. Even a high-priority task must wait before it can access a shared peripheral. This coordination is the job of semaphores and mutexes. In this tutorial, we will see how to use semaphores in FreeRTOS. We will cover both types, binary semaphores and counting semaphores. We will also look at the advantages of using semaphores, the drawbacks of binary semaphores specifically, and how mutexes overcome those drawbacks. Before we start the project, let's go over what a semaphore is, and how it works. There are 2 types of semaphores in FreeRTOS. The first is a binary semaphore, which has only one token. It can be either 0 or 1. When a task takes the semaphore, the count drops to 0. When the task releases the semaphore, the count rises back to 1. To understand why this is useful, consider the following scenario. Suppose we have 2 tasks, one of high priority and one of low priority. Both tasks want to use the UART peripheral to send data. Now imagine that the low priority task is in the middle of sending data when the high priority task preempts it, and also begins sending data. At that point, the data in the UART peripheral will get corrupted because 2 tasks are writing to it simultaneously. To prevent this, we can use a binary semaphore to block access to the shared resource, that is UART in our case. Here is how it works. The low priority task first takes the semaphore, then begins sending its data. The high priority task preempts it, and also tries to take the semaphore. However, since the semaphore is already taken by the low priority task, the high priority task has no choice but to wait. Once the low priority task finishes its UART transmission and releases the semaphore, the high priority task can immediately acquire it and begin transmitting. This way, we effectively place a semaphore wall around the shared resource, ensuring that only one task can access it at a time. The second type is the counting semaphore. Here, instead of just one token, it has multiple tokens. For example, if we have 3 shared resources, we can create a counting semaphore with a total count of 3. Now suppose we have 5 tasks competing for those 3 resources. Since there are only 3 tokens available, only 3 tasks can acquire the semaphore and access the resources. The remaining 2 tasks have no choice but to wait, regardless of their priority. If a task does not hold the semaphore, it cannot access the resource. We will see this in practice in this video. Now that we understand what the binary and counting semaphores are, let's implement them in the project. Let's start by opening Cube IDE. The project from the previous video, Part 3, is already loaded. Let us first rename it to Part 4. While renaming, make sure the Update References box is checked so that the name change is applied at all relevant locations. Alright, the renaming has been done. Now delete the debug configuration from the previous project, and rename the IOC file to Part 4 as well. Next, open CubeMX and load the Part 4 project. This is essentially the Part 3 project with just the name changed. Go to FreeRTOS Tasks and Queues. Here you can see the tasks from the previous project. We need 3 tasks, but we are going to rename them. Let's modify task 1 first. We will name it LPT, which stands for Low Priority Task, and set its priority to below normal. Make sure the stack size is large enough, since we will be using printf to print logs to the serial console. Also update the entry function name to match. Now let's modify task 2. We will name it MPT, which stands for Medium Priority Task, and set its priority to normal, which is higher than LPT. The stack size should again be 512 words, since we will also use printf in this task. Finally, task 3 will be the high priority task, so its priority should be set to above normal, making it higher than both of the other tasks. Our 3 tasks are now ready. Let's also delete the queue from the previous project since we no longer need it. Now go to timers and semaphores. Here you can see separate sections for creating binary semaphores and counting semaphores. We will start with the binary semaphore. Keep the name as my binary sem01. The initial state determines whether the semaphore starts as available or depleted. As mentioned earlier, a binary semaphore has a maximum count of 1, so it is either available or it is not. If we set the initial state to available, the first task that tries to take it will succeed immediately. If we set it to depleted, the semaphore must be released by some task before any other task can acquire it. We will set it to available so tasks can acquire it without any issues. Keep the allocation set to dynamic so the semaphore takes its memory from the FreeRTOS heap. Now if you look at the FreeRTOS heap usage, you will see an error because we have exceeded the configured heap size. Go back to the parameter settings and increase the heap size to around 10 kilobytes. The error should now be gone. The UART is already configured from the previous project, which we will use to route printf output to the serial console. That is all the configuration we need. Let's click Generate Code to generate the project. Alright, let's open the Cube IDE again. You can see the project has been updated with the new tasks. Let's first take a look at the main function. Here you can see the semaphore has been created using the function OS semaphore new. Its max count is 1 and its initial count is also 1. The max count is always 1 for a binary semaphore, and the initial count is 1 because we set it to available in CubeMX. So by default, the semaphore is available for any task to take. We have our three tasks, LPT, MPT, and HPT. Now let's scroll down and write the task functions. Let's start with LPT. Here I am going to define a wait variable, which will be controlled inside the infinite loop. The task will first print an entry log to the serial console, then call OS semaphore acquire to acquire the semaphore. Since the semaphore is already available, it can be taken immediately. The first parameter of this function is the handle of the binary semaphore. The second parameter is the timeout, and this is important. It determines how long the function will wait for the semaphore to become available before exiting. If we set it to 0 and the semaphore is not available, the function will immediately return with an error. On the other hand, if we set it to OS wait forever, the function will block the task indefinitely until the semaphore becomes available. This is how it should actually be used. Since we want to block access to the shared resource, we must wait forever, so the task waits until it can safely acquire the semaphore. Once the semaphore is acquired, the task will print another log, and then simulate resource usage by decrementing the wait variable inside an empty loop, until it reaches 0. During this time the task is actively running, simulating a resource being used by LPT. Once the wait variable reaches 0, the loop exits and the task prints a log, indicating it has finished accessing the resource. Finally, it releases the semaphore using OS semaphore release, after which the task goes to sleep so other tasks can run. Now let's write MPT, the medium priority task. The structure here is largely the same. It first prints an entry log, then tries to acquire the semaphore with OS wait forever. Once acquired, MPT simply prints a completion log and releases the semaphore. It is not simulating any resource usage or waiting inside a loop, it just needs the semaphore in order to print the completion message. So what we want to observe here is this: if LPT has acquired the semaphore, and is busy inside the wait loop simulating resource access, can MPT, which has higher priority, is able to preempt LPT, and print its completion message. That is what we are going to find out. We also have the high priority task, HPT, which we will not use for resource access in this example. We will simply print one log from it so we know it ran. This task does not need the semaphore at all, so it will not block, it will simply run and continue. This is an important point to understand: even though LPT holds the semaphore, it does not block the RTOS scheduler entirely. The semaphore only blocks tasks that actually try to acquire it. A task that does not need the semaphore can run freely, regardless of who holds it. HPT is a perfect example of this. It has the highest priority and does not need the semaphore, so it will always run without any interference. Let's build the project and flash it to the board, so we can observe the output on the console. I will be using the Arduino IDE serial monitor for the output, because it has a timestamp feature, which will help us understand the exact sequence of events and their timing. Let me reset the board once so we can observe the output from the beginning. Alright, let's go through what is happening here. Everything starts with HPT running first, which is expected since it has the highest priority. Once it goes to sleep, MPT runs. Since the semaphore is available by default, MPT acquires it, completes its operation, and releases it. After that, LPT runs, acquires the semaphore that was just released by MPT, and begins simulating resource usage by entering the empty while loop, which runs for around 5 seconds. Now, MPT has a delay of only 200 milliseconds, so it wakes up again well before LPT finishes. It tries to acquire the semaphore, but since LPT is still holding it, MPT is forced into a blocked state, waiting for the semaphore to be released. Meanwhile, looking at the timestamps, you can see HPT continues to run every 1 second because it does not need the semaphore, and is completely unaffected by who holds it. After around 5 seconds, LPT finishes its loop, releases the semaphore, and as soon as that happens, MPT acquires it, completes its operation, and releases it again. So this demonstrates exactly how a binary semaphore works. After LPT acquires the semaphore and begins accessing the shared resource, MPT cannot preempt it to access that same resource, despite having higher priority. LPT, despite being the lowest priority task, can safely hold off a higher priority task from accessing the shared resource, for as long as it needs to. At the same time, HPT runs freely throughout because it never needed the semaphore to begin with. This is the core behavior of a binary semaphore. It ensures that only one task can access a shared resource at a time, and task priority alone is not enough to bypass that protection. Now let's see what happens when we modify the task behavior a little. Inside LPT, I am going to reduce the wait time so the empty loop now runs for around 1 second. The value of 1 million corresponds to approximately 1 second on this development board at its current clock speed. The rest of the function remains the same as before. Inside MPT, we will also implement a wait cycle, but this time MPT will not acquire the semaphore at all, it will simply run the empty while loop for around 5 seconds on its own. Since MPT does not need the semaphore, it can run freely even when LPT is holding it. HPT, on the other hand, will now be the task that needs the semaphore. It will acquire it, print some logs, and release it. Let's build and flash the project to the board. Let me reset it so we can observe the output from the beginning. Alright, so here we can see HPT runs first, which is expected. The semaphore was available by default, so HPT acquires it, runs its task, and releases it. After HPT goes to sleep, MPT starts running its empty while loop for around 5 seconds. During this time, HPT wakes up periodically, it preempts MPT, acquires the semaphore, runs its task, and releases it. This keeps repeating. Now, notice that LPT does not appear in the logs at all during this period. The reason is that MPT is running its empty while loop and has not entered a blocking state, so the scheduler never gets a chance to run LPT. HPT can still run because it has higher priority than MPT and can preempt it, but LPT simply cannot get any CPU time until MPT finishes. Once MPT finishes its loop, LPT finally gets to run. It acquires the semaphore, which is available at this point, and begins running its own empty while loop for 1 second. During that time, HPT wakes up and tries to acquire the semaphore, but since LPT is holding it, HPT is forced into a blocked state. Now MPT also wakes up and starts running its loop again. Since MPT does not need the semaphore, it preempts LPT. Now we have a situation where LPT is preempted by MPT and therefore it cannot finish its loop. Also the HPT is blocked waiting for the semaphore, and MPT is running freely without holding any semaphore at all. Technically, LPT should have released the semaphore after 1 second, which would have unblocked HPT. But because MPT preempted LPT before that could happen, LPT cannot run, cannot release the semaphore, and therefore HPT remains blocked, waiting on a medium priority task that is not even holding the semaphore. This is exactly what is called priority inversion. A medium priority task is effectively making a high priority task wait, not because it holds any resource the high priority task needs, but simply because it is occupying the CPU and blocking the task that does hold the resource. This is one of the most significant issues when using binary semaphores in FreeRTOS. Priority inversion can be solved by using a mutex instead of a binary semaphore. A mutex supports a feature called priority inheritance, where the priority of the task currently holding the mutex is temporarily raised to match the priority of the highest priority task waiting for it. This prevents lower or medium priority tasks from starving a high priority task that is waiting. We will cover mutexes and priority inheritance in detail in the next tutorial. For now, I hope the behavior of the binary semaphore is clear. We will now move on to counting semaphores, which allow us to protect access to multiple resources simultaneously by using more than one token. Let's go back to CubeMX to configure the counting semaphore. Inside CubeMX, I am going to add one more task called VHPT, which stands for Very High Priority Task. Its priority is higher than all the other tasks we have created so far. Now go to the Timers and Semaphores tab, and we will create a new counting semaphore. I am setting the max count to 3, meaning there can be a total of 3 tokens inside it, and the initial count is also 3, meaning all 3 tokens are available by default. Now remember, we have 4 tasks but only 3 tokens, so we will see how these 4 tasks compete for 3 resources using these tokens. Our goal is to ensure that no 2 tasks can access the same resource at the same time. Let's generate the project and go back to Cube IDE. I am going to make some changes to the code. Here I have a resource array which holds 3 resources, and all 4 tasks will compete to access them. There is also a character array that tracks resource ownership, indicating which resource is currently held by which task. The function getResource will be called by a task to gain access to a resource, and similarly releaseResource will be called to release it. The function printResourceTable will print the current state of all resources, showing which task holds which resource at any given point in time. Now I am going to make changes inside all 4 task functions. Let's start with LPT first. Define a resource ID variable. Then inside the infinite loop, the task will first print an entry log and then try to acquire the counting semaphore. After acquiring the semaphore, it calls getResource to claim one of the available resources, prints a log, and then calls printResourceTable, so we can see the current ownership of all resources. It then enters a blocking state for 2 seconds, simulating active use of the resource. Finally, it calls releaseResource to free the resource, and then releases the semaphore token as well. Now let's do the same for MPT. The structure is exactly the same: define the resource ID, acquire the semaphore, get the resource, print the log and resource table, block for 2 seconds, then release the resource and the semaphore. The only difference is the task name. We will follow the same pattern for HPT and VHPT as well. All 4 tasks behave identically in terms of flow, the only thing that differs is the task name. What we want to verify is that no 2 tasks ever hold the same resource at the same time. Let's build the project and flash it to the board. We do not need the Arduino IDE for this, let's just use a regular serial console. Let me run this for a while so we can observe the output. It started with VHPT running first, which is expected since it has the highest priority. It acquired the semaphore, accessed the first resource, 111. The resource table shows that the resource 1 is held by VHPT, while the other 2 are free. After acquiring the resource, VHPT enters a blocking state for around 2 seconds. Within that time, HPT runs, acquires the semaphore, and accesses the next available resource, 222. The resource table reflects this. After HPT goes into the blocking state, MPT runs and acquires resource 3, and again the resource table confirms this. Now all 3 tokens are held by VHPT, HPT, and MPT respectively. At this point, LPT runs and tries to acquire the semaphore, but all 3 tokens are already taken. So LPT has no choice but to wait. While LPT is waiting, VHPT finishes its blocking period, releases the resource and the semaphore token. It then immediately preempts the LPT to start its next cycle. This keeps happening, but at some point you can see LPT also gets access to a resource. The access to the 3 resources keeps cycling among all 4 tasks, it is not limited to the 3 higher priority tasks. Every task gets access eventually, but only one task can hold one resource at any given time, which is exactly what we wanted to achieve. You can think of these resources as 3 instances of a UART, 3 ADCs, or any combination of peripherals. Generally, peripherals are the kind of shared resources that produce errors when accessed by multiple tasks simultaneously, so using counting semaphores or binary semaphores is the right approach to protect them. A mutex works very similarly to a binary semaphore. It has a count of 1, and a task must acquire it before accessing a shared resource. But there is one key difference: ownership. With a binary semaphore, any task can release it, even if it was not the one that took it. A mutex does not allow that. Only the task that acquired the mutex can release it. This makes a mutex much safer for resource protection, because there is no risk of another task accidentally freeing a resource that is still in use. But the real reason we are here is priority inheritance, the feature that actually solves priority inversion. When a high priority task starts waiting for a mutex that a low priority task holds, the RTOS automatically raises the low priority task's priority to match the waiting task. This prevents any medium priority task from jumping in and starving the low priority task. The low priority task finishes quickly, releases the mutex, and the high priority task gets it without delay. We will use the exact same scenario from the previous video to demonstrate this. Same 3 tasks, same code structure, just with a mutex instead of a binary semaphore. So, let's start by opening the Cube IDE first. Here I have the project from the previous video. There are 3 tasks. The low priority task acquires the semaphore, and simulates resource usage by running an empty while loop for around 1 second. The medium priority task does not need the semaphore, so it can preempt the low priority task whenever it wants. It simply runs an empty while loop for around 5 seconds. On the other hand, the high priority task does need the semaphore to print its success message, so it has to wait to acquire the semaphore from the low priority task, while the low priority task is still holding it. Let's flash this project to the board so we can see the priority inversion problem that we covered in the last video. Alright, I'm going to step through to the main point here. This is the line where the low priority task actually runs. It acquires the semaphore and starts using the resource. The low priority task will use the resource for 1 second, but before that happens, the high priority task wakes up and tries to acquire the semaphore. However, the semaphore is already held by the low priority task, so the high priority task has to wait, which is expected behavior so far. But within that waiting period, the medium priority task wakes up, and since it does not need the semaphore, it simply preempts the low priority task and starts running its empty while loop. Now here's the real problem: after 1 second, the low priority task is ready to release the semaphore, but it cannot get the CPU back, because the medium priority task is still running its empty while loop for 5 seconds. So the high priority task has no choice but to wait for the medium priority task to finish first. This means the high priority task is being blocked by the medium priority task, not because the medium priority task holds the semaphore, but simply because it is starving the low priority task of CPU time. This is exactly what priority inversion is. The priorities of the high priority task and the medium priority task appear to be reversed. The high priority task is waiting while the medium priority task is running. To solve this issue of priority inversion, we use the mutex, which we will look at now. But first, let's rename our project to RTOS Part 5. Also, make sure you check the Update References box, so the renaming is applied at all the required places. Alright, the renaming is done. Next, we'll delete the debug configuration from the previous project, and also rename the IOC file to Part 5. Now open STM32 CubeMX and load the Part 5 project into it. We will keep things similar to part 4, I'm not changing anything, so we still have 4 tasks with different priorities. We don't need the semaphores anymore, so let's go to the Semaphores tab and delete them. Now go to the Mutex tab. Here you can see there are 2 different types of mutexes available, one is the simple mutex, and the other is the recursive mutex. We will cover the recursive mutex later in the video, but first let's configure the simple mutex. Click Add to add the mutex, leave its name as my mutex 01, and keep the allocation set to dynamic, so it takes memory from the RTOS heap. That's all the changes we need to make here. Now click Generate Code to generate the updated project. Now let's go back to Cube IDE. Here we can see in the main function, the mutex has been created using the function OS mutex new. Unlike a semaphore, where we had the option to make it either available or depleted by default, a mutex is always available by default with a count of 1, so any task that needs it, can simply call the acquire function to acquire it. We have our 4 tasks here, which we will now update. There is not much to change here. Instead of acquiring the semaphore, we will now call OS mutex acquire to acquire the mutex. The first parameter of this function is the mutex handle, and the second parameter is the timeout. The timeout works in the same way as it did for the semaphore. The function will wait for the mutex to become available. If we set the timeout to 0 and the mutex is not available, the function will immediately return with an error. Using OS wait forever is always a better option, because this way the task's execution will be blocked until the mutex becomes available. After acquiring the mutex, the low priority task will simulate resource usage by running an empty loop for around 1 second, and then it will call OS mutex release to release the acquired mutex. The medium priority task does not need the mutex, it will simply run its while loop without waiting for the mutex. The high priority task does need the mutex to print its success message, and after acquiring the mutex it will release it back. Now, we will also make use of the very high priority task. Here, we will print the priorities of all 3 tasks periodically. I'm using the function OS_thread_getPriority to fetch the current priority of each task. This task runs every 50 milliseconds, so we will be able to observe the priority changes in real time. Let's also change the printed text from semaphore to mutex in the task messages, otherwise it might cause confusion. That's all the changes we need to make. Let's flash this updated project to the board to see the output. Here you can see the processing starts with the very high priority task printing the priorities of all 3 tasks. The low priority task has a priority of 16, the medium task has 24, and the high task has 32. After the very high priority task finishes printing, the high task runs, acquires the mutex, prints its success message, releases the mutex, and goes back to sleep. This is exactly how it worked with the semaphore as well. After the high priority task goes to sleep, the medium task starts running. Since it does not need the mutex, it simply runs its empty while loop for around 5 seconds. Now I'll skip ahead to the part where priority inheritance actually comes into play. That happens when the low priority task finally gets CPU time. Here it is. Once the medium task finishes its loop and goes to sleep, the low priority task runs and acquires the mutex. After acquiring the mutex, the low task starts simulating resource usage by running its empty loop for 1 second. At this point, you can see the priorities are still the same. The low task has a priority of 16, while the medium task has a priority of 24. But as soon as the high priority task wakes up and tries to acquire the mutex, the priority of the low task suddenly rises to 32. This is exactly what mutexes are designed for, the priority of the task holding the mutex, which is the low priority task in this case, rises to match the highest priority among all tasks waiting for that mutex. So initially the low task had a priority of 16, but as soon as the high task started waiting for the mutex, the low task's priority was raised to match it. Now, when the medium priority task wakes up, it cannot preempt the low task anymore, because the low task now has a higher priority than the medium task. This prevents the medium priority task from interfering. After 1 second of resource usage, the low priority task finishes, releases the mutex, and the high priority task acquires it and continues its execution as usual. Note that after releasing the mutex, the priority is switched back to what it originally was. This priority boost is only temporary, and this mechanism is called priority inheritance, where the low priority task inherits the priority of the highest task waiting for the mutex. So we saw how using a mutex prevents priority inversion by implementing priority inheritance. Now that we've covered basic mutex usage, let's look at how recursive mutexes work. But before that, let's understand what recursive mutexes are, and why they are needed. Imagine a situation where a task acquires a mutex, and then somewhere deeper in its execution, it tries to acquire the same mutex again. With a simple mutex, this will cause a deadlock. The task is waiting for the mutex to be released, but the same task is the one holding it, so it will wait forever and never make progress. This is where the recursive mutex comes in. A recursive mutex can be acquired multiple times by the same task without causing a deadlock. The key difference is that a recursive mutex keeps account of how many times it has been acquired by the owning task. Every time the same task acquires it, the count increases, and every time the task releases it, the count decreases. The mutex is only truly released and made available to other tasks when the count reaches 0. So the rule with recursive mutexes is straightforward: for every acquire call, there must be a corresponding release call. If a task acquires the recursive mutex 3 times, it must also release it 3 times before another task can acquire it. A common scenario where this is useful is file handling. Imagine a task calls write function, which acquires a mutex to safely write to a file. Internally, the write function calls another function to allocate a block on the file system, which in turn calls one more function to update the file system metadata. Both of these functions also try to acquire the same mutex to protect the shared file system resource. With a simple mutex, this would immediately deadlock. This is because the allocate block function is waiting for the mutex to be released, but the write function is still holding it. With a recursive mutex, each nested call simply increments the count, and proceeds safely. As each function finishes and releases the mutex, the count decrements until it reaches 0, and only then does the mutex become available to other tasks. Alright, now that we understand what recursive mutexes are, let's go to CubeMX and add a recursive mutex to the project. Now click Generate Code to generate the project again. Here in the main function, you can see the recursive mutex is created using the same function OS mutex new. Now I'm going to make some changes to the tasks. I don't need all the tasks running here, so I'm going to comment out everything except the low priority task. But make sure you leave the delay part, otherwise the very high priority task will keep running and never give CPU time to other tasks. Now we will add 2 functions to the project, function A and function B. Function A runs first, it acquires the mutex, and note that I am still using the handle of the simple mutex here. This is intentional. We will first demonstrate the problem that occurs when you try to use a normal mutex for recursive purposes, and then we will see how the recursive mutex solves it. So after acquiring the mutex, function A prints a success message and then calls function B. Function B will then try to acquire the same mutex again. If it succeeds, it will simulate some resource usage with a 100 millisecond delay, and then release the mutex. Control then returns back to function A, which releases the mutex it acquired, bringing the mutex count back to 0 and making it available to other tasks. Inside the low priority task, we simply call function A, which in turn calls function B. Let's also add a 5-second delay here, so the output doesn't repeat too frequently. Alright, let's build and flash this project to the board. Here on the serial console you can see that function A tries to lock the mutex and succeeds. But when function B tries to acquire the same mutex, it fails and there is nothing printed after that. What has happened here is a deadlock. The mutex is already held by the same task, and since a simple mutex has no awareness of which task is holding it, it simply blocks and waits forever. So we cannot acquire the same simple mutex again if it is already acquired by the same task. To solve this issue we have the recursive mutex. So now we will replace the simple mutex handle with the recursive mutex handle, and run the project again to see the difference. Now you can see that function A acquires the mutex, and then function B also successfully acquires the same mutex again. Finally, function B releases the mutex first, and then function A releases it. So we are able to acquire the same mutex multiple times, and you can do this as many times as needed, depending on how deeply nested your function calls are. This is exactly where recursive mutexes are useful. So to summarize this video, we saw how a mutex solves the priority inversion problem that we had with semaphores, by implementing priority inheritance. We also saw how recursive mutexes solve the deadlock problem that occurs when the same task tries to acquire a simple mutex more than once. Semaphores are great for signaling between tasks, and mutexes are the right choice when you need to protect a shared resource. But both of them have one limitation: they can only represent a single condition. Either the semaphore is available, or it is not. So what if you have multiple events happening at the same time, and you want a task to react to any one of them, or wait for all of them before doing something? That is where event flags come in. Let me explain how event flags actually work. Internally, an event group is just a 32-bit value. Each bit in that value represents a different event. When an event occurs, the corresponding bit is set to 1. When it is cleared, it goes back to 0. Now, FreeRTOS reserves the top 8 bits for internal use, so you have 24 bits available for your own events. That means you can track up to 24 different events using a single event group. You define your flags like this, each flag setting 1 bit in the event group. Each flag is just a unique bit position. When sensor 1 fires, bit 0 gets set. When sensor 2 fires, bit 1 gets set. And so on. Now here is where it gets interesting. When a task waits for event flags, it has 2 options. It can wait for any of the specified flags, meaning it unblocks as soon as at least 1 flag is set. Or it can wait for all of the specified flags, meaning it only unblocks when every single flag it is waiting for has been set. This is something a semaphore simply cannot do. With a semaphore, you can only wait for one thing at a time. With event flags, you have full control over when your task wakes up. You can tell it to sleep until every single expected event has occurred, or you can tell it to react the moment the first event comes in. That flexibility is what makes event flags so powerful in real embedded applications. In this video, we will cover 3 things. First, we will see how to use event flags to wait for all 3 sensor events before processing. Then, we will switch to waiting for any single event, and see how to identify which event actually triggered the task. Finally, we will look at a practical example where a button press and a UART receive both trigger their respective tasks directly from an interrupt service routine. Let's open the Cube IDE. Here I have the project from the previous part, which is part 5. The first thing we will do is rename this project to part 6. Make sure you check the Update References box while renaming, so the name gets changed at all relevant locations. Alright, the renaming is done. Now delete the debug configuration file and also rename the IOC file to part 6. Next, open STM32 CubeMX and load the Part 6 project into it. It is essentially the Part 5 project, just the name has been changed to Part 6. Now open Middleware, FreeRTOS, and go to the Tasks and Queues tab. The 4 tasks from the previous project are still here, so we are going to delete all of them and create 4 new tasks for this tutorial. Task 1, Task 2, and Task 3 will be used to set the event flags, while Task 4 will read those flags and print the data on the serial console accordingly. All 4 tasks will have normal priority and a stack size of 512 words. Now go to the Mutexes tab and delete the mutexes that were created in the previous project, as we do not need them anymore. Next, open the Event Flags tab. Here we will add one event group. Leave the name as MyEvent01. Also keep the allocation dynamic, so the event group will take its memory from the FreeRTOS heap. If we check the heap usage, we still have enough heap available, so we are good to go. That is all we need to configure here. Click Generate Code to generate the project. Alright, the project has been generated, so let's go back to Cube IDE. Here, inside the main function, you can see our 4 tasks have been created, and below that the event group is also created using the function OS event flags new. Now scroll down to the tasks. Let me first delete the leftover code from the previous project. Now, each task will set 1 bit of the event flag, so let's define those bits first. Task 1 will set bit 0, Task 2 will set bit 1, and Task 3 will set bit 2 of the event flag. Now inside Task 1, we will first print a log message on the serial console, and then call OS event flags, set to set bit 0 of the event flag. Note that if you want to set multiple bits at the same time, you can OR them together. For example, ORing task 1 bit and task 2 bit will set both bit 0 and bit 1 in a single call. But for now, we are only setting bit 0, which indicates that the event was generated by task 1. Let's also add a delay at the end so the other tasks get a chance to run. Similarly, task 2 will set bit 1 and task 3 will set bit 2 of the event flag, each with their own separate delays. Now, task 4 will read the event flags. We will first print a log message indicating that the control is inside task 4, and then call OS event flags wait for the events. This function takes 4 parameters. The first is the event group handle. The second is the set of flags we want to wait for. Here we are providing all 3 flags. The third parameter decides how the function waits for these flags. If you use OS flags wait any, the task will unblock as soon as any one of the 3 events is generated. If you use OS flags wait all, the task will wait until all 3 events have been generated. So even if task 1 sets its flag, the function will continue waiting for task 2 and task 3 as well. By default, the flags are automatically cleared once they are read by this function. However, if you do not want them cleared automatically, you can OR in the OS flags no clear option. The fourth parameter is the timeout. If you set it to 0 and the event has not been generated yet, the function will immediately return an error. If you set it to OS wait forever, the task will remain blocked until all the required events are generated. We are going to use OS wait forever, which is the right approach here. After the events have been read, we will print a success message on the console. Alright, let's test this much first. Build the project and flash it to the board. Now open the serial console to view the logs. Here you can see that the processing task was waiting for the events first. Then task 1 generated its event, task 2 did the same, and task 3 also generated its event. Once all 3 events were generated, the processing task printed a success message indicating it has received all the events. The same process repeats again. Task 1 generates its event, task 2 follows, task 3 does the same, and once all three are set, the processing task prints the success message again. This confirms that the event flags are being cleared and reset properly after each cycle. So waiting for all events works just fine. The task waits until all three events are generated before proceeding. This can be useful in situations where you have different sensors reading current, voltage, and temperature separately, and you want to combine their data to generate a single output. For example, imagine a power monitoring system, where you need readings from all three sensors, before you can calculate the total power consumption. If you processed each sensor reading individually, your output would be incomplete. But with event flags, you can ensure that your processing task only runs once all three sensors have reported their data, giving you a complete and accurate result every time. Now, it is worth mentioning that waiting for all events does not mean you have to wait for every single event in the group. You can choose to wait for only task 1 and task 2 events, and completely ignore task 3 if you do not care about it. Now that we understand how waiting for all events works, let's see how we can use the same tasks but wait for any one of those events instead. So instead of using OS flags wait all, we will use OS flags wait any. In that case, the function will succeed as soon as any one of the three events is generated. I also want to print which particular event was triggered, so we need to make a small change here. The OS event flags wait function returns the flag value containing the event data. We will store that return value in a 32-bit variable, and then check which particular bit is set in that variable. Based on that, we will print a log message telling us which task generated the event. Now with the current logic, task 1 would keep firing every second and dominate the output, so let me give each task a separate delay. Task 1 will run every 3 seconds, task 2 will run every 5 seconds, and task 3 will run every 7 seconds. Alright, let's flash this updated project to the board and see the output on the console. You can see that task 1 generated the event first, and the processing task read it correctly. Then when task 2 generated its event, the processing task printed that as well. And when task 3 generated its event, it printed that too. So the processing task is now succeeding whenever any one of the three tasks generates an event. Notice how the processing task does not wait for the other two tasks anymore. As soon as one event comes in, it handles it immediately and then goes back to waiting for the next one. This is a much more responsive behavior compared to waiting for all events, and it is very useful in situations where each event needs to be handled independently as soon as it occurs. Now let's take a practical scenario where we can use these event flags. We are going to use a button to blink an LED, and add another task to print the data received over UART. The idea is simple: when the button is pressed, an interrupt will be triggered, which will set an event flag. The button task will be waiting on that flag, and as soon as it is set, it will toggle the LED. Similarly, when data is received over UART, another interrupt will fire, set a different event flag, and the UART task will wake up, read the data, and print it on the serial console. This way, both events are handled independently using a single event group. Let's go back to CubeMX and make some changes. First, in the Tasks and Queues tab, we will create a button task with a low stack size. Since it will not print anything, it will simply turn the LED on or off. We will also create a UART task with a stack size of 512 words, because it will use printf to send the received data to the serial console. Now let's configure the hardware. I am going to use pin PA3 to connect the button. The button will be connected between this pin and ground. So set this pin as an external interrupt, so that whenever the button is pressed, an interrupt will be triggered. By default this pin will be pulled high using the internal pull-up, and when the button is pressed it will be pulled down to ground. Make sure you also enable the interrupt for the XD3 line. Now let's look at the UART settings. The low power UART 1 is already enabled for logging. Here we are simply enabling its interrupt so we can also receive data from the computer in the interrupt mode. That is all the changes we need to make. Click Generate Code to generate the updated project. Alright, the new tasks have been created here. Let's go to the top of the main file. Here we are going to define two more event bits. One is the button pressed bit, which will set bit 3 of the event flag, and the other is the UART received bit, which will set bit 4 of the event flag. We will also define a buffer array here to store the data received from the UART. Now let's set up the interrupt callbacks. When the button is pressed, pin PA3 will go low, an interrupt will trigger, and the GPIOXD callback will be called. Inside this callback, we will simply call OS event flags, set to set the button pressed flag. Similarly, when data is received on UART1, another interrupt will trigger and the UART RX complete callback will be called. Inside this callback, we will set the UART received bit of the event flag. Now inside the main function, before the FreeRTOS scheduler starts, we will call HAL UART receive interrupt to receive 5 bytes in interrupt mode. One important thing to note here is that the HAL library automatically disables the UART receive interrupt after a single callback. So if you want to keep receiving data continuously, you must call receive interrupt again at the end of every RX complete callback. If you forget to do this, the interrupt will fire only once and then stop working. Now let's scroll down to the tasks. Inside the button task, we will call OS event flags wait for the button pressed event generated by the XD callback. Since we are only waiting for one flag here, it does not matter whether you use OS flags wait all, or OS flags wait any, both will behave the same way. The task will remain blocked until the button is pressed and the flag is set, and after that it will simply toggle pin PB7 where the LED is connected. We will also add a small delay here to prevent button debouncing. Similarly, inside the UART task, we will wait for the UART received event, and once that flag is set, we will print the received data on the serial console. That is all the changes we need to make. Let's build and flash the project to the board. Let's test the button first. You can see that every time I press the button, the LED toggles. That means the button press is successfully generating the interrupt, which sets the button pressed flag, and the task is reacting to that event and toggling the LED. Now let's test the UART event. I am going to send 5 bytes of data to the STM32 from the computer. And you can see the data has been printed on the serial console. So when the 5 bytes are received, the UART interrupt fires, the UART received flag is set, and the corresponding task wakes up and prints the data. So in this video we saw how to use event flags as a notification mechanism between tasks, and between interrupts and tasks. In this video, we are going to look at something a little different, software timers. Let me start by explaining what a software timer actually is. In a typical embedded system, if you want to do something repeatedly, for example, blink an LED every 500 milliseconds, you would normally use a hardware timer. But hardware timers are a limited resource. Your microcontroller only has a few of them, and they are often already in use for other purposes, such as PWM generation or input capture. A software timer solves this problem by relying on just one hardware timer underneath, managed by FreeRTOS, and allowing you to create as many virtual timers on top of it as you need. Each software timer can call a function, known as a callback function, when its time period expires. Now, there are two types of software timers, a periodic timer and a one-shot timer. A periodic timer keeps repeating. Once the time period expires, the callback function runs, the timer resets, and it starts counting again. This cycle continues indefinitely, or until you explicitly stop it. A one-shot timer, on the other hand, fires only once. After the period expires and the callback runs, the timer stops on its own. If you want it to run again, you have to restart it manually. Now, there is one important thing to understand about how these timers actually work inside FreeRTOS. FreeRTOS does not run the timer callbacks inside your task or inside an interrupt. Instead, it uses a dedicated background task called the timer daemon task, also referred to as the timer service task. Whenever a timer expires, FreeRTOS sends a message to this daemon task through a queue, and the daemon task is then responsible for calling the appropriate callback function. This has a couple of important implications. First, your callback function should be short and should never block. If you place a long delay inside a timer callback, it will hold up the daemon task, and delay all other timer callbacks that are waiting in the queue. Second, the priority of the timer daemon task matters. If its priority is set lower than your other tasks, the callbacks may not fire on time. We will keep these points in mind as we go through the example. In this video, we will cover three things. First, we will create a periodic timer that prints the logs at a fixed interval. Then, we will create a one-shot timer that triggers once after a set delay. And finally, we will see how to start, stop, and reset a software timer from within a task. Let's open CubeMX and set up the project. We are going to create a new project for this video. Go to Middleware and enable FreeRTOS with CMSys version 2. Leave the basic configuration parameters at their default values, as we have already covered those in earlier videos. Now go to the Tasks and Queues section. A default task is already created here with normal priority, and a stack size of 128 words. We will be using this default task in our project, so leave it as it is. Next, go to the Timers and Semaphores tab. Here you will find a dedicated section for software timers where you can add new ones. We will create both of our timers from this section. Click Add to create the first timer. In the Type field, you will see two options, periodic and one-shot. We will create the periodic timer first, so select periodic. Set the timer name to periodic timer, and the callback function name to PT callback. Leave the remaining settings at their defaults, and make sure the allocation is set to dynamic, so the timer allocates its memory from the FreeRTOS heap. Click Add again to create the second timer. This time, select one-shot as the type. Name it one-shot timer and set its callback function to OST callback. Leave everything else at the default values. Both timers are now created, and we already have our default task in place. If you go to the FreeRTOS heap usage section, you can see that around 2 kilobytes of heap memory is still available, so this configuration is perfectly fine to work with. We will also be printing logs to the serial console, so we need to enable a UART peripheral. On the Nucleo L496 board, the ST-Link virtual COM port is connected to low-power UART1, so enable this peripheral in asynchronous mode. Configure it with a baud rate of 115200, 8-bit word length, no parity, and 1 stop bit. By default, CubeMX assigns pins PC0 and PC1 to LP UART1. However, if you check the schematic of the L496 board, you will notice that the ST-Link RX and TX lines are actually connected to pins PG7 and PG8. So we need to reassign LP UART1 to use PG7 and PG8 instead. Next, I am also going to connect a button to the pin PA3, so configure this pin as a GPIO input. There is also an onboard blue LED connected to pin PB7, set this pin as a GPIO output. You can see in the board schematic, the blue LED is connected to the pin PB7. Now go to System Core and open the GPIO configuration. Set the button pin to pull-up mode. This means the pin will read high by default, and when the button is pressed, it will be pulled low. That transition from high to low is what we will use to detect a button press. Since we are using FreeRTOS, we also need to change the HAL time-base source away from sys-tick. This is because FreeRTOS uses sys-tick internally for its own tick management, so the HAL layer needs a separate, dedicated time-base to avoid any conflict. Here, we are selecting timer 6, which is a basic general-purpose timer with minimal features. You can choose any other available timer as well, the important thing is just that it is separate from sys-tick. Next, go to FreeRTOS Advanced Settings, and make sure the new library entrant option is enabled. This ensures that standard C library functions like printf work correctly in a multi-threaded FreeRTOS environment, where multiple tasks could potentially call such functions at the same time. Now go to Project Manager, set the toolchain to STM32 Cube IDE, give the project a name, and click Generate Code. Once the code has been generated, we will import the project into Cube IDE. The project has now been imported, and we can see the main file of our new project. If you look at the main function, you can see that CubeMX has already generated the initialization code for both timers, the periodic timer and the one-shot timer, along with the default task that we will be working with. Now scroll down to the task function. Keep in mind that while both timers have been created, they do not start automatically. We need to start them manually from within our code. When execution enters the default task, the first thing we will do is start the periodic timer. To do this, we call the function OSTimerStart. Since this line runs only once at the beginning of the task, before the infinite loop, it is the right place to start the periodic timer, as it is designed to run continuously and repeat on its own. This function takes two parameters. The first is the timer handle, which in our case is the periodic timer handle. The second is the time interval in milliseconds, which determines how often the callback function is called. We are setting this to 1000 milliseconds, meaning the periodic timer callback will be triggered once every second. Inside this callback, you can perform various lightweight operations, such as setting event flags or printing a short message to the console. In our case, we are simply printing a log message to indicate that the periodic timer callback has been called. As mentioned earlier, always keep timer callbacks short and non-blocking. After starting the periodic timer, the task enters its infinite loop. Inside this loop, we continuously check for a button press. If pin PA3 reads low, it means the button has been pressed and the pin has been pulled to ground. When that happens, we turn the LED on by setting pin PB7 high, and then start the one-shot timer using OSTimerStart, this time with a delay of 5000 milliseconds. This means the one-shot timer will expire 5 seconds after the button is pressed. Once it expires, the OST callback function is called. Inside this callback, we turn the LED off by resetting pin PB7, and print a log message to confirm that the one-shot timer has fired and the callback has executed. Since we are using printf, make sure to include the standard I/O header file at the top of your source file. We will also use our custom retarget function to redirect printf output through LPWAT1, so that the log messages appear correctly on the serial console. That is all the code we need for this example. Let's go ahead and build the project. The build completes with no errors, so we are ready to flash the firmware to the board. Open the serial console to view the logs. You can see that the periodic timer callback is printing a message every 1 second. This confirms that the periodic timer is running correctly, and its callback is triggering at the expected interval. Now let's press the button. As you can see, the LED on the STM32 Nucleo board has turned on, indicating that the button press was detected, and the one-shot timer has started. We will now wait for 5 seconds. The LED has turned off, and the corresponding log message has appeared on the console. This confirms the expected behavior. When the button was pressed, the one-shot timer started counting. After 5 seconds, the timer expired, the OST callback function was called, the LED was turned off, and the log message was printed. Now let's explore something interesting. What happens if we keep pressing the button before the 5 seconds are up? Every time the button is pressed, the timer start function is called again for the one-shot timer. This does not create a new timer or stack multiple timers on top of each other, it simply resets the existing one, pushing the expiry point forward by another 5 seconds from the moment of the latest press. As long as we keep pressing the button within the 5-second window, the timer keeps getting reset, it never expires, and the callback is never triggered. This behavior makes the one-shot timer particularly useful for scenarios like debounce logic, or inactivity detection. It also works well as a lightweight alternative to a watchdog timer, and since it integrates naturally with FreeRTOS, it fits cleanly into a multitasking application without any extra complexity. Now, just like starting a timer, we can also stop a running timer and check whether it is currently active. For example, when the button is pressed, we can check if the periodic timer is currently running by calling the function OS_timer is running. This function returns 1, if the timer is active and currently counting. If it is running, we then call OS_timer stop to stop it immediately. To restart it at a later point, we call OS_timer start again. We do this inside the one-shot timer callback. Once the 5 seconds have elapsed and the callback fires, we check if the periodic timer is stopped, which is indicated by OS_timer is running returning 0. If it is stopped, we restart it with a 1-second interval, and it resumes running as normal. Let's test this behavior. You can see the periodic timer is running correctly, and printing a log message every second. Now when we press the button, the periodic timer logs have stopped appearing on the console, confirming that the timer has been successfully stopped. After 5 seconds, the one-shot timer expires, its callback runs, and the periodic timer is restarted. The log messages begin appearing on the console again, exactly as expected. So I hope you now have a clear understanding of how software timers work in FreeRTOS. In this video, we are going to examine something that directly affects every single task you create in your system, the stack. Let me begin by explaining why understanding the stack is important for your projects. Every FreeRTOS task has its own dedicated stack. When a task uses more stack memory than what was originally allocated to it, the excess data overflows into adjacent memory areas, which corrupts that data and causes unpredictable system crashes. Stack overflows represent one of the most common problems encountered in RTOS-based systems, and they are also among the most difficult issues to find and fix. FreeRTOS provides 2 helpful tools to assist you in managing and preventing stack problems. The first tool is OS thread get stack space, which allows you to continuously monitor how much stack memory remains available so you can adjust and optimize your stack sizes accordingly. The second tool is the stack overflow hook, a special function that detects and catches overflow events while your program is running. Now, there is one important concept you should understand clearly. The free stack value that OS thread get stack space returns is called the high water mark. It represents the minimum amount of free stack that has ever been recorded for that particular task. This value tells you the worst-case scenario for stack usage in your task. Here is something surprising: certain function calls like printf actually use much more stack space than you might initially expect. A single printf call alone can consume around 150 bytes of stack just for its internal buffers, and this happens regardless of how long your text string is. This is precisely why stack sizes should always be determined by actively monitoring your system during the development and testing phase. In this video, we will cover 3 main topics. First, we will create a monitor task that tracks and records the stack usage of all your other tasks. Second, we will enable Stack Overflow detection in CubeMX so your system can catch problems automatically. And finally, we will write and implement the Stack Overflow hook function that activates whenever an overflow is detected in your system. Let me start with the project from part 7. I have already loaded it and opened it in the STM32 Cube IDE. The first thing we will do is rename the project to RTOS Part 8. Make sure you check the update reference box, so that the name change is applied at all relevant locations throughout the project. Alright, the renaming is now complete. Next, delete the configuration file and rename the IOC file to Part 8 as well. Now open STM32 CubeMX and load the renamed project. This is basically the same Part 7 project, only renamed to Part 8 for this lesson. You can see that we already have GPIO output pin configured for the LED, and a low power UART configured for the virtual COM port connection. We will use both of these components in our project. There is also an input pin configured for the button. We will not use the button in today's project, but let's keep it in place anyway for potential future use. Now go to the middleware section, and then select FreeRTOS. Here we will make some important changes from the previous project. Open the Include Parameters section. You can see the parameter called UX_Task_Get_Stack high watermark is already enabled by default. We need this parameter because it allows us to monitor the maximum stack usage of each individual task and detect potential stack overflow risks before they cause problems. Since it's already enabled, we don't need to make any additional changes here. In the Tasks and Queues section, you will see the default task that was already created from the previous project. We will rename it to Task 1 and set it to normal priority. The stack size is currently 128 words, which we will keep. Let's also rename the entry function to match. Leave all other settings at their default values and make sure the location is set to dynamic so the task can take memory from the FreeRTOS heap when it needs it. Now we will create a second task. Name it Task 2 with the same normal priority level, but set the stack size to 256 words, which is twice the size of Task 1's stack. Create a third task called Task 3 with normal priority and a stack size of 512 words, which is twice the size of Task 2's stack. Now create a fourth task, which will be our monitor task. Give it a low priority setting so it doesn't interfere with the other tasks while they are running. Since this task will only observe and monitor stack availability in the other tasks, its priority should be the lowest among all tasks. Give it a larger stack size so it can perform all its monitoring operations without any issues. Now we have 4 tasks in total, 3 with normal priority and the monitor task with the lowest priority. The monitor task will measure and report the remaining stack space available in the other 3 tasks. Let me quickly delete the timers that were created in the previous video since we no longer need them for this project. If you go to the FreeRTOS heap usage section, you'll see that we've already exceeded our originally allocated heap space. Go back to the Config Parameters tab and increase the total heap size to around 10 kilobytes to give ourselves enough memory. You can see that the heap error is now gone, so we're good to proceed with the project. That's all we need to configure in CubeMX. Go to the Project Manager tab and click Generate Code to create the new project files. The project has been generated successfully, and in the main file, you can see all 4 different tasks that we configured in CubeMX. Now let's scroll down to the Task Functions section. I need to delete the leftover code from the previous project that we no longer need. We will first observe how much stack space is available when we don't make any changes to these tasks. However, we still need to write the monitor task function, which will retrieve the stack space information from the other 3 tasks. Inside the monitor task function, we will create 3 variables to store the available stack space of the 3 tasks. Next, we will use the function called OSThreadGetStackSpace to retrieve the available space currently remaining in any of the tasks. There is also another related function called OSThreadGetStackSize, which returns the total amount of stack memory that a task has been allocated. However, the OSThreadGetStackSpace function specifically returns only the available space remaining in the task's stack. So we will use the OSThreadGetStackSpace function for our monitoring purpose. The parameter that this function requires is the task handle. We simply need to provide the respective handle of the task we want to monitor. After we fetch the stack space information for all 3 tasks, we will print this information to the serial console so we can view it on our computer. Since we don't want this monitor task to run very frequently and use up processing power, we'll add a delay of 5 seconds before the task prints the information again. That's all we need to do for now. Let's build this project and check for errors. There are no errors in the build, so let me flash it to the board and test it. Open the serial console viewer, and here we will see the results from our monitor task. We need to wait at least 5 seconds for the monitor task to print the first result. Here we have the stack space information from all 3 tasks displayed in bytes. Task 1 has 384 bytes of available stack space, Task 2 has 896 bytes of available stack space, and Task 3 has 1920 bytes of free stack space available. These numbers show us how much room each task has before it would run out of stack memory. Note that we have not written any code inside these tasks yet, so what we're seeing is basically the maximum stack space available for each of these tasks. It's important to understand that these numbers might vary significantly depending on the specific microcontroller you're using, and how your memory is configured. For example, F7 and F1 series boards may have different amounts of total RAM available, which directly affects how much stack space you can safely allocate to each task. That's why it is essential for you to monitor the stack usage according to your specific microcontroller, and the unique requirements of your project, and based on those measurements, you can make informed decisions about how much stack space each task needs, and how much code you can safely write inside it without causing problems. Now let me try to add code that prints information from task 1 on the serial console, and we'll do this every 2 seconds. We will then observe how much stack space is still remaining, and free in task 1 after using the printf function for printing. Here you can see that task 1 is printing data every 2 seconds on the console, and the available stack space has been reduced to only 196 bytes. This means that approximately 188 bytes are being occupied by the printf function, and its internal operations. It's important to note that this is not a fixed number, and might vary depending on which microcontroller you're using. Also, here's something worth remembering: the actual size of the string doesn't matter. Whether you print a single character or a very long string, the memory consumed by the printf function remains almost exactly the same, because printf reserves internal buffers regardless of string length. Now that we know 196 bytes of space are still available in task 1, let me create a local array that is 100 bytes in size and check how much additional memory is consumed by this array. Let's flash this updated project to the board again and observe the results. Here you can see that the free stack space has been reduced further to 92 bytes, which means 104 bytes are now occupied by the array we just created. Even though the array is only 100 bytes, an additional 4 bytes were used for stack frame overhead, and alignment padding that the compiler adds automatically. Now, what happens if we make this array much larger, let's say 200 bytes instead? We already know from our calculations that there isn't enough space available in the task stack to safely handle this much data. But let's try it anyway, and see what happens to the system. You can see that the monitor task is simply printing that the stack space is 0 bytes, which indicates a serious problem. However, notice that the task is still running and continuing to execute its code, and that's happening simply because we're not actively accessing or writing data to that memory location. We only created the array declaration, and without actually performing any read or write operations on that memory area, the rest of the task's code continues to run normally. This situation perfectly highlights the real danger of Stack Overflow. It doesn't always cause an immediate system fault or crash. Instead, it can silently cause data corruption in adjacent memory areas and create unpredictable behavior throughout your system until the corrupted memory is actually accessed or used by the processor. This is why early detection is so critical. Now we know how to monitor the stack usage effectively. To prevent memory faults and system crashes due to Stack Overflow, we can implement a Stack Overflow hook. This hook function gets called automatically when a stack overflow is detected by the system. FreeRTOS provides a special hook function to handle stack overflow detection automatically. If you look in the config parameters section under the hook function related definitions category, you can see there is a feature called Check for Stack Overflow Hook, which is disabled by default. There are two different options available for detecting stack overflow, Option 1 and Option 2. Option 1 performs a check to see if the stack pointer has gone out of bounds at the time of every task context switch. This method is faster but may miss overflows that happen between context switches. Option 2 performs additional checks on the stack by using a pattern or marker value placed at the end of the stack. This method is more thorough and can catch overflows more reliably, but it uses slightly more processing power. We will use Option 2 for our project because it provides better detection accuracy. If you look at the details below the option selection, you can see that when you select either Option 1 or Option 2, a function called the application stack overflow hook is automatically created and generated inside the FreeRTOS.c file. The developer needs to write the actual implementation code inside this function to decide what should happen when an overflow is detected. Let's generate this updated project again in CubeMX. Now go back to Cube IDE and open the FreeRTOS.c file, which is located in the source directory of your project. Here you can see the function that was generated by CubeMX. Inside this function, we need to add code to handle the stack overflow error appropriately. This function has two parameters provided to us. The first parameter is the task handler of the specific task whose stack has overflowed, and the second parameter is the name of that task as a string. Depending on what operation you want to perform, you can use either the task handle or the task name to identify which task caused the problem. To prevent FreeRTOS from hanging the system or performing unpredictable operations after detecting an overflow, we should call an infinite loop inside this function. This infinite loop prevents the control flow from leaving the function and returning to other tasks, which could cause further corruption or crashes. Let's quickly test what happens now with this stack overflow hook in place. The only addition to our system is this stack overflow hook function with an infinite loop inside it. Here you can see that nothing is being printed on the console anymore, which tells us that none of the tasks are running their code. This is because the control flow has entered the overflow hook function and then immediately entered the infinite loop, stopping all other task execution. Other than running this infinite loop, we can also print some diagnostic logs that indicate exactly which task caused the stack overflow. For that, I'm going to use the printf function to print the task name on the serial console. Note that the printf function may not work properly in this interrupt-like context, but I want to demonstrate this approach before we move to a more reliable solution. Let's also include the standard IO header file so we can use printf, and then flash the project to the board again. Here you can see a little bit of data from task 1 got printed normally, but when the overflow occurred, nothing is printing on the console anymore. This happens because printf relies on internal buffering and complex interrupt-driven mechanisms that may not function properly when called from the stack overflow hook. In this critical error state, we need to use lower-level UART transmission methods that are more reliable and don't depend on the standard library's buffering system. Let me first declare the UART handler as an external variable so we can access it from the hook function. Now, inside the overflow hook function, we will first to initialize the UART hardware and then reinitialize it back to a known working state. This ensures that the UART is ready to transmit data. Next, we'll prepare the data to be transmitted via UART. For this, I'm going to call the sprintf function to load the error message along with the task name into a character array. Finally, we'll call the HAL UART transmit function to send this array directly to the computer via the serial connection. Let's build and flash this updated project to the board again. Here you can see the log message is now printed successfully, clearly indicating that there is a stack overflow that was caused by task 1. Let me reset the board again to see the message clearly. Now you can see it clearly states that a stack overflow has been detected in task 1. After this log message is printed, the control entered the infinite loop, and therefore the other tasks are not running anymore. Now let me quickly reduce the stack memory being occupied by task 1 back to a safe level, and flash the project again to the board. Now you can see the logs are printing normally without any issues or warnings. This means the overflow hook function is not being called anymore, which indicates that task 1 is operating within its allocated stack space. So I hope you now understand how to monitor task stack usage in FreeRTOS, and how to handle stack overflow situations. We saw how to use the OS thread getStackSpace function to monitor the remaining stack space in your tasks. We also enabled the stack overflow detection feature in CubeMX, and implemented the hook function to catch stack overflow errors, and log them to the serial console using direct UART transmission. That is it for this video. You can download the project from the article linked in the description of this video. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.